Welcome to the third lesson of this video series on complex analysis, and we are continuing our discussion in understanding what is complex analysis. And in this video we are particularly covering what is a complex number along with some great interesting historical amazing facts, the difference between complex and imaginary number, which comes often as a confusion between students and individual, the complex operations, and something more. The earlier first and the second videos have been primarily on the history of complex analysis, how complex analysis, imaginary numbers, etc. they were discovered, and now we are going into the real mathematics of complex analysis, and this video we are covering those topics, and it would be very easy, simple, with a lot of examples, illustrations taken, so that the concept of complex analysis is very clear and you find it super interesting to study. My name is Shaunak and you are watching this video on my channel Physics for Students. A warm welcome to lesson 3 of complex analysis. First, we would just like to have a quick glance on the topics. So we are going to understand what is a complex number, some amazing facts, how complex numbers emerged, the difference between complex and imaginary number, complex plane and how it can be described on the geometric pattern, and some of the operations with complex numbers. So having laid these topics, first we will like to understand what is a complex number. Now, the world around us that we see are mostly numbers like 10, pi, -2 and 1.2 square root of 2. These are practically something which we call as real numbers. So the objects that we count, the cycles that we see are often, mostly are covered by real numbers, and this real number is denoted by this capital, or you can say it is a blackboard capital. This is called an R. So we are mostly watching people or things around us which are real numbers. Okay, so you see the real number can be plotted around a kind of a time on a line, which are the real numbers with the positive and negative. And if I square a real number, it gives to 4, and further it gives to things. So we are more or less acquainted mentally with what we call a real numbers. So as time and history progressed, we also found out something which are called imaginary numbers, and those are denoted by I, which is called the iota sign, and 2i squared equals to 4, and so on. So if we see any solution to a quadratic of the form ax squared plus bx plus c, so from our school level mathematics we know that it is denoted by this: x equal to minus b plus minus b square minus 4a upon 2a, 4ac upon 2a. So it would yield to two solutions. Now if you're I'm trying to give you a basic approach so that you can understand how complex numbers emerge. So if we try to solve the problem x squared plus 5x plus 10 equals to 0, so what we get is this, and we get further this, and we get this odd thing, that is square root of minus 50. Now what is that? Now, can we have a real number whose square leads to this number, just the way we saw just now, like 2 square equals to 4 and minus 2 square? This is the basic concept, and this is where complex numbers come in. So particular quadratic form or a solution, and where we can find something which is a number which doesn't have anything which will lead to another number. This is where the complex numbers come in. You can watch my earlier first and especially the first video on complex analysis, gives a complete historical background and details on the emergence of complex numbers. Now these complex numbers have many applications in physics, chemistry, biology, electrical engineering, and even finance and economics. So there is no point that we can ignore the study of complex numbers. Okay, so if we, from this definition, that is this one, if we get square root of 15 is not real, right? And this is the definition of imaginary unit number. So we define the unit number I as a square root of -1, that is I equals to square root of -1. So if we get something like this, square root of -15, so we multiply by 1 and we get I equals to 15, which is more or less we can tell that it is something which is similar to 3.879. Okay, so the definition of imaginary number: a number is said to be imaginary if the square is negative, obviously. So square root of minus 15 is an imaginary number. Why? Because it leads to negative minus 15. So square root of 15 is an imaginary number, because if we do the further calculation, you see then we first square root it, then square root of 1 squared, then multiplied by 15, it ultimately leads to 50. Now here comes a very interesting fact. Now the use of I or the iota to denote the imaginary unit number is used in most scientific fields. Now in electrical engineering, chances are that you know it as J, because I in electrical engineering is a variable denoting the electric current. So be aware that that is basically electric current. Okay, now we will try to completely define a complex number. A complex number is any number written in the form z equals to a plus bi, where a and b are the real part, and this is the these are the real part. Sorry, a, b, and this is the imaginary part, I. Right, and we use acronyms. So don't worry if you come across those acronyms. It is real, or RE sometimes called, which is the A, and the imaginary part Z. So it is called, that is how things are. Now the entire family of complex numbers is denoted by this double or little bit bold C, and we write it as this. So a real number is a complex number without any imaginary part. Okay, so far so good. So there is another important fact. This gentleman, whose name is Gerolamo Cardano, was an Italian polymath, and in 1545 in his book Ars Magna he made the first systematic use of negative numbers in Europe, published with attribution the solutions of other mathematicians, and it acknowledged the existence of imaginary numbers. To know further, I would request you to please go back to my first video on complex analysis, where a complete detailed understanding of the emergence of imaginary numbers and the emergence of complex number and the history are given. Okay, so if we solve for the equation of x, for example, x squared plus 5x plus 10 equals to 0, then what we get from here is this and this and this and this. So we see what here is that a real number has no imaginary part, and an imaginary part has no real part. So I mean to say, we will soon see this. Don't worry what it is actually it's all about. So this is just to give you an idea that if we solve this equation further and we get the value minus 5 upon 2 plus minus square root of 15 upon 2i. So you see the real number has no imaginary part, and imaginary part has no real part. Okay. The question is that if we find this something, can we plot it on a graph? Can we find it on a graphical pattern? So there is a very nice way to graphically represent complex number, as long as you realize that real numbers and imaginary numbers are exclusive. That means a real number has no imaginary part and an imaginary number has no real part. Let's see in the next part. So this is a quite clear depiction. You can see using the complex plane we can visualize any complex number z as a point on a two-dimensional plane. Here it is here represented as z equals to 3 plus 5i. Okay, now here comes something very interesting. This is called a complex number and imaginary number, and I won't say it is a kind of a confusion, but often among students or aspirants you will see that you want to know what the difference or anything about it. So first of all, you see imaginary number is always expressed as any real number multiplied to an imaginary unit, like these numbers 3i minus 2i pi, right? So these are the real part and we get the imaginary part. So if we can say imaginary number equals to iy, where y is the imaginary part, and complex numbers are imaginary numbers plus numbers that has both real and imaginary parts. For example, these numbers. So you can see that this is the complex number which has got an imaginary part as well as a real part. Let us see in the next part with some more examples. So 6 plus 8i, this is a real part, this is an imaginary part, and it has got an addition sign, that is the plus. Okay, and if I write it as a plus bi, so note that if the real part, this real part actually goes 0, then it becomes bi, which is, it becomes imaginary, and that's lovely, and it doesn't have a real part. So if we equate the real part to 0, the entire equation or the expression becomes imaginary. So what we can say is that imaginary numbers are numbers that can be written as a real number multiplied by the imaginary unit I, and complex number and imaginary numbers plus numbers that has both real and imaginary parts. I is both imaginary and complex, the iota sign. So here is a kind of a graphical depiction of how the entire number family resides. So we start with counting numbers 1, 2, 3, 4. Then we get whole numbers, then we get integers, then you see the green part is a rational number, then the algebraic numbers come on the outer circle 9 plus 5 dot I, pure imaginary, okay, we will explain later what is a pure imaginary, and there are complex numbers. So imaginary numbers can be said as a subset of complex numbers, and complex numbers are all set of all points lying on Argand plane. We know what is an Argand plane. We saw it I think in the second part of the video. And imaginary number on collection on imaginary axis. Only the imaginary number are collection which points on the imaginary axis of Argand plane. Okay. We now need to understand that all these numbers, they reside on something which is called a complex plane. So let us see quickly that what actually is a complex plane. So if you see, this is a real number line from positive and negative. So this is the real number, this is the real number. So if I get an expression something like 3 plus 4i, then where do we put this number? Right? We cannot find any place where we can put this number. So imaginary number goes up and down. That means if we get a kind of an axis like this, okay, then imaginary number, we have to go 3 steps on the right, 1, 2, 3, and then further 4 steps on the top, and we plot 3 plus 4i somewhere here, right? So this is how we can place an imaginary number, because on a real number line we cannot find any place to put it. So we move 3 parts positive and then 4 parts towards the imaginary axis, that it goes up. So 3 units up and 4 units at the imaginary axis. Further, we can see this example 4 minus 2i. Again, we move towards 4 steps towards the x-axis, but because it has got a negative sign before the imaginary number, we move down and we place it somewhere here. So 4 units along and 2 units down. So complex plane, what we can say is, because it's a combination of real and imaginary number, and why it is plane? Because it's a geometric plane, and we are measuring it for the to remove complexities in 2-dimensional. Okay, so here it is again a kind of an graphical depiction of z equals to 3 plus 5i. So you see z and 3 is in the real axis, and this goes to the imaginary axis. So here is a definition of complex plane. Complex plane we can visualize as being a point in the complex plane such that the x-axis represents the real part and the y-axis represents the imaginary part. So here you see that in general ordinary vectors are denoted by an arrow. So if I denote this 3 plus 4i as a vector, yeah, this is interesting, then we can do the addition and multiplication using the parallelogram or the addition multiplication rule. So 3 plus 5i plus 4 minus 3i, that can leads to 7 plus 2i. And if we consider the same and we use it in a polar form, you see we get an angle of 0.927. And the question is that complex number 3 plus 4i can also be shown at a distance of 5 and which has an angle of 0.927 radians. Question is that how do we get into 0.927 radians? Now just to tell you that although in this series we have not covered polar form, but if you go back to my playlist of quantum mechanics, mathematics of quantum mechanics, I have been covering some part of complex analysis but not that details, where I have covered the polar form which you want and go. But anyway, from 3 plus 4i, and if we use the distance formula and plot those values in this way to square root of 25, we get 5, right? And we know that theta equals to tan inverse of y upon x, from where we get a value of 0.927. That's simple. Now this is 0.927. Now if we use the polar formula x equal to r cos theta, and if you put the value of 0.927 over there, then we get a value which is approximately 3, right? And this 3 corresponds to this one. And with y equal to r sine theta, if we plot the same value 0.927, we get approximately 4, which is this one. Right? You can take a pause to note the calculations over here. So what we do is that complex number written in polar form is this, and it can be written further in a neat form as r cos theta plus I sine theta, which can be written as x plus I y, and this I sine theta is written as r cis theta. So what we can do, we can write this as 3 plus 4i 5 cis 0.927, and you see here that we got the value of 0.927. So that is how the radians etc. are calculated. If you want to go back, you can, I think you can go back over here. Yeah, here you see that the value 0.927 is there. So the complex number is shown at a distance phi and at an angle of 0.927, and this is how the entire calculation comes. We plot the values with the tan inverse, and from there we write it in polar form, and we write it as this one. So the theta is replaced by 0.927 and 5 ci is replaced as usual. Okay, so there is another important interesting fact coming up, that complex numbers are essentially, we call it as an extension of real numbers, right? But a question comes is that, is there any extension to complex numbers? Because these are real number extended, so can we extend complex numbers? Yes, and these are called Quaternion, and it is denoted by this capital H. So Quaternion are a number system extending complex number with the important distinction that they are non-commutative. So AB won't be equal to BA. And just like complex numbers can be visualized as being a point on a plane, Quaternions are points of four-dimensional hyperspace. So Quaternions are useful in terms of applied mathematics, physics, computer graphics, and computer vision. So next question we can obviously ask that, is there an extension for Quaternions? Yes, obviously there it is, and they are called Octonions, and is represented by this capital O. Right, so not only are Octonions non-commutative, they are also non-associative, right? So this is how it is. It's not equals to C, it's not equals to A. It is not necessarily it will be equal to, so Octonions can be seen as an 8-dimensional hyperspace. Now if you ask the next question, that is there an extension of Octonions? So mathematics is still now we don't have anything. So that's a very important fact. Okay, so finally what we do is that we will catch up and wrap up with some simple operations with complex numbers. These are pretty simple. I think you have already done through your fresh course. So if you consider z equals to a plus bi, we can define this complex addition as this. The law we will come to the later part of the video, commutativity and associativity we will talk. And if we define complex multiplication as this, then it is AC minus BD plus AD plus BCI. So what we have done, we have taken the real part and imaginary part together, and we have taken the first, outer, inner, last kind of a method. So let us take few examples. If you want to add this, we get minus 1 plus 4i, and this leads to minus 5 minus 5i. So I'm not going to explain step by step. As you understand, these are pretty simple, you might have done. Here is an important concept coming up, complex conjugate, which is very useful otherwise in mathematics as well as in, I would say, quantum physics uses a lot of complex conjugate. So it is denoted by Z or Z with a star or an asterisk, and this is known as vinculum, which was introduced by the mathematician Franz von Schouten around 1646. So we define the complex conjugate as Z equals to A minus Bi. So the complex conjugate of a complex number is the number with equal real and imaginary part, but the magnitude is opposite. So here are the two matrices. You see 3 plus I, and the sign changes to minus to plus. So the complex conjugate of one matrix with complex entries is another matrix whose entries are the complex conjugates of other matrix. Some more examples. If you see this, then it becomes 5 minus 10i, 3 minus 2i becomes 3 plus 2i. But here is an interesting thing. If z equals to minus 3, then the complex conjugate will also be minus 3, right? So we call it the complex conjugate of a real number is itself. And here you see, if I get z equals to 2i and then z equals to minus 2i, that means the complex conjugate of an imaginary number is minus itself. These are two exceptions. I mean to say, you can just take a note of that. Okay, so that's it for today's video. I would like to thank you very much for watching, because we will continue more on complex analysis. Please do subscribe and help me to grow. Click on the bell icon and click on all to get all the notification from Physics for Students. If you want, I am available over this email ID. You can write for any further clarification on any mathematics and physics problem, obviously, which I know. I have a specialized channel on YouTube, that is General Relativity Explained, where I explain mostly mathematics and physics exclusive to Einstein's general theory of relativity. And you can follow me further on my Instagram, Facebook and LinkedIn profiles. That's all for today's video. Please do put up the comment, and what I will do next is that we are going to continue with this wonderful concept of complex analysis further in this video. Till then, goodbye and may God be with you.